Dear students, in this video, we're going to consider RS flip-flops, different types of flip-flops like D-type flip-flop, T-type flip-flop, the Jacob flip-flop. So the flip-flop are used extensively in digital electronics for various applications we'll be looking at throughout this chapter. So let's start with the RS flip-flop. So the name flip-flop itself means it's changing state from high to low. But what flip-flop means? So flip-flop is changing state. So through flip-flops, we want to have a means to control when these devices, these electronic hardware change state. And by controlling these state changing, we can achieve certain very interesting applications. Okay. Now, before we get into flip-flop, let's just look at some terminology that we will come across. As you can see here on the waveform, we are looking at a clock cycle or a waveform which is changing state from, for this one is changing from low to high, and this one is from high to low. So this one is called a positive edge and this one's a negative edge. So why we're studying that? Because we're going to see some circuits are going to be sensitive to the rising edge. This is called a rising edge with positive edge, and this one is going. Some circuits will be sensitive to falling edge. So we're going to see later how do we actually show that on circuits so that we know is a particular pin, is a particular input sensitive to a falling edge or to a rising edge. Okay, so let's consider the first type of flip-flop. It's called the RS flip-flop. R stands for reset and S stands for set. So basically you're trying to find, to study a hardware device which allows us to set the output high or to reset it to low. So let's consider this circuit here, which is composed of two NAND gates are shown and is connected in a very specific way, as you can see here. So we have an input here. We are tentatively calling that one as S and this one as R. But when we study the behavior of this circuit, we're going to see whether actually this pin does a setting or this one does a resetting, or do we need to switch the pin label. So for the time being, we're calling this one S and R. And you can see here the outputs is Q and Q bar. So we expect these two outputs to have complementary states, means opposite states. So if this is high, you want this one to be low. If this is low, you want this one to be high. Okay, and you can see the output of this one now is connected back to one of the inputs of this NAND gate G2, and similarly Q bar is connected to one of the inputs of the NAND gate G1. So let's study what happens when we have such a configuration. So let's first start with a case where both Q is equal to 1 and Q bar is equal to 1. Let's say we had a case like this where your Q and Q bar were 1. We were saying Q and Q bar should have different states, but let's try to enforce and see what happens if they had the same state. So I'm just going to annotate. So we are saying at this point is this is 1 and this is 1 is also is 1. Okay, so S and R now can have different states. So let's say we put this S here at 1. We're considering different combinations, and then at some point we're going to see, we will understand actually how this circuit behaves. So we're just considering different combinations for time being. Let's assume we have a state where this is 1 and this is 1. Okay, so what happens here if you feed back this this Q bar is 1, so this input also become 1, and for a NAND gate we know that when S is 1 and when the two inputs are 1, this has to become 0. So it means in that condition here this will become 0. So you're feeding back this 0 here, this becomes 0, and then this will become 1. Yep. So what do we see here is if your S is 1 and R is 1, the two outputs here, Q and Q bar, needs to be different state. They can't be the same state. Okay, so let's consider the opposite now. What if we considered Q first? Okay, so I'm just going to clear all the drawings. So let's consider again this to be 1, this to be 1, and let's say now we consider both to be 1 again. Now, what happens if, remember, in the example just considered, we fed back Q bar and this became 1. What if we fed back this one now and says this is 1? We find this becomes 0 now. Okay, and this is fed back, so this becomes 0 and this stays 1. Yep. So what do we find here? In this case, we find that the states have to be different, like we said earlier. But in this case, we find Q bar is 0 and Q is 1 now, which was opposite to what we had earlier. So which is which? It depends what was the previous state of the system. So this device here we have memory. So when you start analyzing this type of circuit, you would have to know what the previous state is. It's not just a question of what's the current state of a system. So if your Q was 1, it's going to remain 1. Okay? and your cue ball would have to have a different state. On the other hand, cue ball could well have been 1, but then Q would have to be 0. So when S is 1 and R is 1, we need to have different states here. So this is one condition we're finding. Okay, so that's what's explained in these notes here. So you can go through what I've just explained to you. So this is part of combination. So when R is high and S is high, we have a previous state, but they have to be different states. Okay, so you can also analyze a circuit with Q is equal to 0 and Q bar is equal to 0. So let's do that. So let's assume again your S is 1. So always considering S is 1 and R is 1. What will happen if this was 0 and this was 0? This is what we're saying. So let's consider this one. So let's see we feedback this 0 here. So this one becomes a 0. So 1 times 0, you would invert it, an AND gate. So this is going to become a 1. And then this one is going to be fed back. 1 times 1 inverted becomes 0. So again, you find that the states have to be different. Okay, so in conclusion, when your S is high and R is high, your output needs to have different states. Now, what would be the actual state of Q and Q bar? It depends on the previous state of this circuit. Yeah, so this could have also been staying at 0 if you consider Q bar here to feedback. If you consider Q to come down here, then you would get the opposite state. Okay? That we've seen in the previous. Okay, so this part of the truth table summarizes very well what we just said is when R is high and S is high, the circuit is going to maintain the previous state and would have different states. So it's not possible for Q and Q bar to have the same state. They need to be different. Okay, so now let's consider a negative going pulse on R and S. So based on what we had earlier, so this diagram shows it very well. So this is more recap. We said S is equal to 1, R is equal to 1. So what are we saying here? In the current state, your Q is equal to 1 and your Q bar is 0. If you just feed back this state, you find that's completely stable state. If you feed back this 1 here, so what you're saying is 1 is coming back here. So you have a 1 here. So 1 times 1 inverted because the NAND gate again, you get 0. So 0 fed back. So 1 times 0, you get your 1 here. Okay, that's a perfectly stable state. Now in this state here, you send, because R is currently a high, you send a negative pulse like this. So your R just comes 0 momentarily. So this is a state here. Your R was 1, it became 0. So what happens now? Let's study how the circuit behaves. So the output of this one, if one of the inputs to your NAND gate is 0, output has to be high. So this becomes high here. You can see it's changed from 0, it has become 1. So this has changed. And then this one is fed back here. 1 times 1, you get 0. So you get the state here. And if you want, you can feed back that 0 here. So again, 0 times 0, you're going to get your 1. So if your R now gets back to high, so if this becomes a high now, this doesn't matter. It's going to still maintain that state here. So in conclusion, if your S was 1 and R was 1, which we said earlier, is a stable state, which allows your Q and Q bar to be at different logical states. If in this condition you made your R become 0, so what will happen? Your Q is going to become 0 and your Q bar will become 1. Okay. Let's go ahead. So what happened here, basically, when you have made your R become active, you can say in this case, your R is active in the falling edge. Like we said at the start of this video, you have inputs sometimes which are sensitive to a falling edge or a rising edge. So in this case, you can see it's the falling edge. Yeah. So when you made your R become active, what happened is your Q, which was 1, it became 0. So you are resetting your Q. You see, you're resetting your Q. Okay? So this is why you have this R there. When you make this pin become active, it's resetting the output Q. So as you're seeing here, so Q was 1, you're resetting it means become 0. Setting means make it become high. Resetting means making it become low. Okay, now let's consider a case where actually your Q was 0 initially and your Q bar was 1. So I'm just going to clear this and just scroll down. Let's consider this case now. So I want to be very detailed here, very meticulous about the way we're going through this. So all in the lecture notes, you have all the possibilities discussed. So make sure you go through this on your own. Now let's consider the next possibility here. So again, we've said if S is equal to 1 and R is equal to 1 is a stable state. And in this state, we're saying now your Q was 0 initially and your Q bar was 1, which is very well possible. So let's see what is the circuit actually stable in this state. So if you feed back this 0 here, you get a 0 here. So 1 times 0 and then inverted, you get a 1, and then you feed back this 1 here. So 1 times 1 inverted, you get a 0. So these two states are stable. As we've concluded above, S equal to 1, R is equal to 1 is a stable state for flip-flop based on NAND gates, and your outputs have to be different states as we're seeing here. So in this state now, if we made our R become low, what happens? Okay, so this is what we see here. Your R was 1, now we are making it become low. We are maintaining our S high. We just change one of the inputs at a time. So if this becomes 0 here, your Q bar, so if one of the inputs to a NAND gate becomes 0, this has to be 1. So this is a 1 here, and then your feedback is 1. So you have a 1 here. 1 times 1, you get 0. So this is stable state. You feedback by 0 if you want here. So again, 0 times 0, you keep getting 1. So in that case, if you made your R become high again, so if that becomes high back, there's no change because 1 times 0 will see the 1. So what are we observing here? If in your initial state your Q was low, it's going to remain low because the R pin's purpose is to reset it. It's already low, so resetting it means it's going to maintain the low state again. Simply because, like I said earlier, resetting means making the output Q become low. It's already low, so it won't have any impact on the state. Okay, so we've done the analysis till now for the pin R. Let's try to see what influence does the pin S have. Okay. So this is what we can conclude in this case here. What we've just studied is if your R now is low and your S is maintained high, your Q would become 0 irrespective of the state. If it was 0, it's going to remain 0. If it was high, it's going to become low. Yeah, as we're seeing here, and your Q bar would always be complementary to Q, so it's going to become high here. So if you do a similar analysis for the S pin, you're going to find now when the S becomes low, actually your output becomes high. So I'll leave it at the stars for you to do. So you can do a very similar analysis to what you've done here. So when you're in this state here, I want you now to analyze what happens when you make S become low. So you're going to find that actually Q becomes high. Your R make Q low. Your S is going to make your Q high. If it was low, it becomes high. If it was high, it remains high. Okay. So in summary, this is what you're going to get for the S pin. When it becomes low, your Q will become high and your Q bar becomes low. Okay. Now, the last combination which we consider, so we considered 3 combinations already. If you just do a summary of these 3 small excerpts, if you want, from the truth table. So one condition where both R and S are high. So you see that the output maintains the previous state and the outputs have to be different states. It's a very stable state. Now, the next state you consider is when your R is low and your S is high. We say that actually this resets your Q, make it become low. If now you made your S low, it actually sets your Q. So the last combination we have to look at is what happens if both S bar and R bar are low. So this is a state which is called the indeterminate state. It's a state where the flip-flop is not stable and it's very unpredictable what state the output will take. Because here we're considering NAND gates, and we know when one of the inputs of a NAND gate is actually low, the output will be high. So in this case here, you are making both Q and Q bar become low, and this is not a state we want. We want Q and Q bar to have different states. So this state where R bar and S bar are both low is called an indeterminate state. We don't actually use that in flip-flops. Okay. So let's just conclude. So this is a full truth table of the flip-flop we just studied using a NAND gauge. So we found that when both the inputs are high, it maintains the previous state, that's fine. When R bar is low, it becomes Q is low, so it's resetting it. When S is now low, it's actually setting your Q high, and L, when both your R and your S are low, is called an indeterminate state. We don't typically use that. Now, if you notice what change did we do to this circuit here? We started with S and R. Now we are saying this S bar and R bar for a simple reason that we found these 2 inputs to be sensitive to the falling edge. What we said is when S becomes low, that it does the setting. Is when R is low, that it does the resetting. It means these 2 pins are active low inputs. Like we said, at the start of class. This is why I have a bar on top here to simplify. But these two inputs will be sensitive to falling edges, means low states. Now, we can very well represent this circuit as follows. We've seen that it's like a black box here where these logic gates are sitting inside. And now if we know the truth table here, we don't need to go to detail of what's inside it. If we just do a behavioral description like we've done earlier, we can also understand how this flip-flop works, but you need to know this as well. So where this behavior is coming from is from these two logic gates collected in that way. Okay, so just to again recap on that, we made S become with a complement here and R complement simply because they are producing the desired effect when they become low, as you can find. When S bar is low, then it is setting the output, and it's when R bar is low that it is resetting the output. So you could represent your RS flip-flop in that way here, and these two pins are active. So as an exercise for you now, I'm just giving this one now. So this is a flip-flop based on NOR gates. So you can do a similar analysis here. I want you to start looking at different combinations of S and R and putting Q and Q bar at different states and seeing what is a stable state for this flip-flop circuit with NOR gates. So one comment about NOR gates, we know the NOR gate, whenever one of the input is high, the output has to be low. Yep. So already this is saying to you that the stable state, the indeterminate state, if you want, would be when S and R are both high, because this is where you are trying to produce Q and Q bar to be both low. Yeah, because we know that's the behavior of a NOR gate. So the stable state is going to be now opposite to what we had with NAND gates, is when S and R bar are both low. Then you can start studying what happens if you set S go to 0, R go to 0 as the initial position to start off, and then you put Q and Q bar both high or both low. You see they have to change state and become different, and then from this point onwards you can make your S become high now and see what happens, and make your R become high now in turn and see what happens, and then you can understand, is it actually an active low signal or active high signal, and the indeterminate state, like we say, is going to be when S and R are both high, because it's trying to produce Q and Q bar to both low. So study the circuit now like we've done earlier in details, and then we're going to look at this back in the tutorial class. Okay, now next topic we look at, so we've just studied this part here of the circuit. We've just said that, if I just annotate, we've just said this is actually an S bar and this is R bar. Yep, so we've just studied this part of the circuit, and we've seen that you can use these two pins there, S bar and R bar, to actually set or reset Q. Now, what we're studying here in that circuit is we're adding a further input called a clock here. Now, what's the purpose of this clock? If we just move up, so it's a clocked RS flip-flop. So what's the purpose of that clock here is, whenever you make a change on S or R, the change would not appear at Q unless when you have a clock. So everything is synchronized to clock. So let me just draw a signal for the clock, just to explain to you how this works. And you will notice it's S bar and then this is S here. We'll also understand what happens now, because when you put an S here, it means now this input here is actually an active high signal. So the desired output, so we know S stands for set. It means when S becomes high now, would we have Q becoming high, and similarly is when R becomes high now, do we have Q becoming low, because R stands for reset. So let me just draw some waveform to use for you. So let's say we draw a small clock signal here. Okay, so these are called the rising edges of the clock. It's a falling edge, rising edge, falling edge, and rising edge. Okay, so what we noticed earlier, based on the previous analysis, we've said, let's say we want to set the flip-flop, so this has to become 0 here to set it. So the question is, when would this this input become low? Okay, so as you can see here, your clock signal is coming up and high. So when we want this change to happen on our output pin, only when the we have a rising edge on the clock. Yeah, so when this becomes, once changes from 0 to 1. So when this pin is 1 here, the question is, when this pin is 1, when do we get this 0 here? Is when this one is also 1, because it's a NAND gate. Okay, so this is why S here is high. It's not complemented, because a desired change to get a 0 here is when S actually is high. So similar comment, if you have your clock which is having rising and falling edges, you want to have a circuit which actually does a desired change only when you have a rising edge. So it's on, for example, if you make S become 1, this 1 would not have effect. So initially, let's say your clock is 0, so you're somewhere here. Okay, you're somewhere here. You have made your S high to try to make Q become high as well. Yeah, because S is for set again. I'm just saying these things again and again so that it's become clear. So S stands for set. Whenever you activate S, you are making Q become high. We've already studied this part of the circuit to see how this happens. So let's say now you made your S high so that you want to make Q become high, but the change would not happen as long as you don't have this rising edge. So at this point here, your clock pin here is 0, as you can see. So if you take 1 times 0, invert, you're going to get a 1 here. So as long as it's 1 here, this will not have the desired change because this pin here is actually active, as we've seen earlier. So if you make your S high and then you wait for that rising edge on the clock, so this changes now from 0 to 1, then you have a condition where it's 1 times 1 inverted, then you get the 0, is then that your Q becomes 1. I hope it's clear what I'm trying to say. So all the changes you're doing on S and R are synchronized to this clock signal here. So similarly, if we do the same analysis for our R pin, so again, I'm drawing the clock here. So I'm just drawing two cycles. So again, you have your rising edge here. So let's say initially you have a 0 here, and then this is 1. So initially your clock is at 0, it's at the low state, so we are somewhere here. And then your R, you want now to reset you. So you are making this one, remember this one was an R bar, as we said earlier. So if you want to reset you, you have to make this one become 0, as I said earlier. Okay, so at this point, you have made your R become high, so that you can make this one become low. But as long as your clock is low here, so you're getting a low signal here, this is going to produce a high here. It's only when your clock becomes high, so this changes to high. Do we have 1 times 1? And then inverted, you get a 0. And once you have R bar 0, this is going to become 0. You're resetting your output. So again, same comment to what we had earlier. This change which you want to bring onto your output would happen only when your clock is having rising edges. So it means by adding this part of a circuit to your RS flip-flop, you first are able to synchronize changes to clock. And in the process, we're seeing now your inputs S and R here are active high. Yeah. When you put a 1 here, you actually set, and when you put a 1 here, you actually reset. So this, if you want to represent this clock RS flip-flop at the block diagram, you have your block diagram like this, a block, and then you have 3 inputs now. The clock is normally shown like this. So you have 3 inputs. So this is going to be your okay, so this is going to be your S pin, your clock pin, and your R pin. Okay, so this is going to be your Q and Q bar as before. So what I'm trying to say here is these 2 pins now are S and R, it's not complemented. Yeah. So when we consider the flip-flops without any additional gates to produce a clocked feature, so this was S bar and R bar. Okay. So similarly, I would want you to analyze, it's part of the tutorial sheet actually, to analyze for this flip-flop here, if I wanted to make the flip-flop based on no gates become a clock RS flip-flop, what type of circuitry you need to add in front. So I want you to do this analysis and see what type of circuitry you get. Now, next thing we look at are other types of flip-flops. So we're not going to look now inside these boxes to see what type of logical gates we're using. You can do that on your own if you want. Definitely these circuits would have logic gates there. It actually uses RS flip-flops to achieve them. But now the approach we're going to take henceforth is we're going to take a behavioral description approach. So we're just going to look at a block diagram like this and give a description of how the circuit behaves when different changes in input pins take place. So this is how the D-type flip-flop looks like. So you have a pin called D, and then you have a clocked pin here. You have preset and clear pins, as you can see here, and your outputs of Q and Q bar. So this is the important part here. If you want to understand how this D-type flip-flop works, this is the description here. In normal operation, the output Q takes the logic state at D at every rising edge of a clock signal. So very simple description of the D-type flip-flop. So it's saying here Q is equal to D at every rising edge of your clock. Yeah. So if you made, for example, D become let's say D0, yeah, and then you have a rising edge, this 0 would be transferred to Q. If you make D equal to 1, similarly, your clock pin here would need to go to a rising edge for the 1 to appear here. Yeah. Now you can find you have 2 pins here called preset and clear. These pins are used initially to set the initial states of your flip-flop. So if you, for example, you activate the preset pin, you're going to make Q high and Q bar low. If you clear, it's going to make your Q become 0 and Q bar 1. So these 2 pins are used to set the initial states of a flip-flop, and then in normal operation, this D and your clock, which is going to allow you to carry out the operation. So what actually do we do with this D-type flip-flop? We're going to look at some applications later. So we have a timing diagram here to first explain what happens. So let's say this is your clock pin here, and this is your D input. So this is a waveform which is appearing on your clock, and this will have a particular frequency. Yeah, and this D here is depending on some process. This could be a door open, door close, or any other process which is having a binary logical state. So what did we say here is Q is equal to D at every rising edge. So you have a rising edge here, your D is 0, so your Q remains 0. Yeah, as a rising edge here, we find your D is remaining low, so your Q is remaining low. And then at some point you have a rising, you have your D changing state from 0 to 1, but the change doesn't occur on Q. It's only at a rising edge that you're going to detect this one, and at this point your Q becomes high. So again, Q is equal to D at every rising edge of your clock. So if you follow through in a similar way here, you find in the meantime between the next, from this rising edge to the next one, we find that your D has become low. So at this point your D becomes low again, and for all these rising edges your D has remained low, so no change in your output Q. And then for the next rising edge for this one, you find that your D actually became high, so your Q becomes high also, and then and so on. Of course your Q bar is just the complement of Q. We've seen that before. The D-type flip-flop, very simple to understand, and you should be able now to understand easily how the D-type flip-flop works. Next type of flip-flop we're going to look at is called a T-type flip-flop. So T stands for toggle. So toggle, in a sense, when we're toggling anything, it means it's changing state. So the T-type flip-flop is going to change state at your output for specific conditions. So let's look at how this works. So again, we have the preset and clear pins. As we've seen earlier, these can be used to set the initial states of Q and Q bar. Now we have a clock pin again, and in this case, in the D-type, we have a D pin. In the T-type, we have a T pin here. Let's see how this works. So if T is low, so I'm just going to annotate here. So what it's saying, if T is low, pulses on the clock does not cause any changes output. So we know our clock is going to be a waveform with a particular frequency for rising and falling edges. Okay, so you have these rising edges here. This is how it's typically shown, rising edges. So we're saying in that state here, when your T is low, pulses on the clock, so your rising edges, does not cause any changes output. So Q is going to maintain its initial state as long as your T is 0. That's what he's saying. Now, next is saying if you made your T becomes high now, if you make this one high, so if T is high, the output Q takes its complementary logic state. Okay, so what he's saying here, if your T is high, and let's say you start with Q is equal to 0, for every rising edge you have here, Q is going to toggle. So it's going to become 1 for this rising edge, as long as T is high, of course. And then at this rising edge, this is going to become 0. At this rising edge is going to become 1. So it means Q takes a complementary state, or the opposite state whenever you have the rising edges, provided T is high. Okay. Let's look at this truth table here to understand it better what's happening. So you can find here if T is high, so you're maintaining T high, the output Q takes its complementary state. So you can see here, if your output was high, it becomes low. If it was low, it becomes high. That's what he's saying. Okay. So let's look at this timing diagram here to get to illustrate this further. So you have your clock pin here, which is having rising and falling edges, and then your T here is 0, then becomes 1, and then becomes 0 again. So what we said is initially let's assume our Q was high, so this can be done using the preset pin. So as long as your Q is low, you don't have any change in state for Q or any rising edges of your clock. But when T is high, whenever you have a rising edge, Q is going to toggle state. So you have your rising edge here, and your T is high, so it changes state from 0 to 1. And again, for next rising edge, your T is still high, so change the state again. For the next rising edge, your T is still high, so change the state again. For the next rising edge, again, your T is high, so change the state. And then now you can see your T pin has become low. So now rising edges does not cause any toggling in your output. This one is a bit more difficult for me to understand, but like I say, its name is toggling. So just to recap, whenever your pin T is high, your output Q would toggle state for every rising edge. Now, the JK flip-flop is nothing new here. It's the JK flip-flop is sort of a universal flip-flop. So from the JK flip-flop, the name is saying JK. So you have an input called J, and output Q is Q bar. But you have an inputs J and K, and then the clock and the preset and the clear here are shown. You can see small change here. You have the small circle here, meaning that these two pins here are active low. You can have JK flip-flops with preset and clear active high as well. So just to illustrate that, if you put a small circle here, a small circle next to a pin means the desired change would occur when this pin becomes low. For example, preset means you want to make Q become high. So how can you make Q becomes high? Is when preset becomes low. Similarly, clear here is to make Q become low. So when you actually do that is when you make clear become low itself, because an active low signal. It's simple. Whenever you see a small node like this, a small circle next to a pin, it means the desired change you want to bring about would occur when you are actually doing it, you are bringing the pin low. It's an active low signal. Okay, so this truth table is having, you can see J, K, and the clock are all don't cares here. This is simply saying what happens when you actually set the state using the preset and the clear. So you can see here when your preset is low, you're actually setting your output. When your clear is low, you're actually clearing output, and when both are low, it's an indeterminate state. You don't want both to be low, and when both are high, as shown here, this is where your device now starts functioning as a JK flip-flop. So if you have already set your initial state based on this truth table, the next step here, you're going to maintain your preset and clear to high state because they're active low signals, and then you can see that when you set J and K both to low, it means this is an off state where you're not doing anything. If you put your J and K at different states, so if for example your J was high and K is low, or vice versa, your JK flip-flop behave like a D-type flip-flop. If you make your J and K both high, your JK flip-flop starts behaving like a D-type flip-flop. So if you use a JK flip-flop, you can implement a D-type and a T-type as well. That's what the function is. It's not really a new flip-flop, it's a universal flip-flop. If you want, using one circuit, you can achieve the function of it too. So I'm stopping here in this video. So the next video is going to look at some applications of these flip-flops where you're going to apply the knowledge we just looked at.